Okay, folks, it's time for our next online lecture, More Physics in the Time of Corona. Today, the plan is to discuss electrodynamics, which basically means when things are moving, stuff moves. And the specific topics today will be Ohm's law and Faraday's law. Those are the main things we're going to talk about today. Okay, so how to introduce this topic? Basically, we want to understand about what happens when we have current and voltage in situations where we have time-dependent fields. Time-dependent fields. And this is a big topic, but let's sort of chop it down, make it smaller, and present it in little pieces. So, an important overall thing to remember is that so far we have been discussing electric. For electrostatics, we discuss E fields, but no current density. And we have been talking about magnetostatics. And in magnetostatics, we were talking about B, which was created from current density, but no electric fields. And so here in electrostatics we had E, but and so I want you to see that for electrostatics we were discussing the relationship between charge density and electric field, but with no J. But for magnetic fields, we were talking about the relationship between B and J, but with no electric field. And so a point that I want to make is that now we have to consider the situation where we have electric field and current density coexisting. And that might seem just sort of trivial, but it's not. It's like, think about it. I mean, before, when we were doing magnetostatics, we had lots of current density creating a magnetic field, but we never had an electric field. But now we have to consider But now we want to consider what happens when we have them both at the same time, electric fields and current density, and that's a big deal, and subtle, and it leads to new topics such as dissipation, which we'll get into. So the first place to start here is to discuss Ohm's law. And so Ohm's law is the first manifestation of this new physics. And so let's talk about Ohm's law. Basically, the question I should ask is, if we have a conductor, there's some conductor, and we have some current flowing through the conductor, then what is the electric field? That's basically the question. And this question it's a pretty simple question, but it's maybe a little bit more, from our electromagnetic point of view, it's a little bit more subtle than you might think, because remember how we've been doing things so far. So far, what we've done is we've done this. We said, well, if I have a conductor, and if I place that conductor into some electric field, then we know what happens is because what happens is that the charge separates. The charge moves in the conductor and separates. Then what happens is we have charge separation, which is also called screening, charge separation, such that E equals 0 in the conductor. And so in the conductor we always have E equals 0, because that's the only way that we can have an equipotential surface, or an equipotential volume. A conductor is an equipotential volume. That's what we've been talking about so far. And what that means is that if I'm in a conductor, if I move from one point in the conductor here, say, to another point with charge, then the charge cannot move downhill. It has to be a level playing field. The energetic landscape has to be constant. And so that means that in conductors so far we've had electric field is 0. And so already you can kind of start seeing how that's going to be a problem for. That means that, so if electric field is 0, then how can we have E and J coexist in a conductor? See, that's so already you can see it's kind of confusing, because the electric fields we've said electric fields are always 0. But now we want to talk about a new situation, and the new situation is what happens if we insist that the electric field is not 0? So what if we insist that E is not equal to 0 in a conductor? And so it's sort of like you say, it's sort of like you're going to say to the conductor, well, I'm going to put an electric field inside of you. And the conductor says, no, I'm an equipotential surface. I'm an equipotential volume. And you say, no, I insist. And how is it that we can insist? How do you do that? This is how. For example, suppose that I take a material, a conductor, and suppose we turn on an electric field, and we put the electric field in that direction, and this is a conductor. Then you know what's going to happen. The positive charge carriers will move. Let's say the positive charge carriers can move. It's actually electrons, but we can just assume it's positive charge carriers. Suppose that they can move. So they're going to start moving. They're going to feel the electric field and move in response. Now, we know what would normally happen. We just have to go up here to see what would normally happen. Up here, normally what would happen is that the charge would separate until the electric field is 0. But now, suppose that I do this. Suppose that I have a little machine, not a little machine, I should say a little man, suppose there's a little man here, and the little man takes the charge in his little grasping fingers, and then he pulls them, and he runs all the way back to the other side, and then he puts them back. And he says, that's what he does. He grabs the charge on one side as it's flowing, and he doesn't let it build up. And he runs to the other side, and he puts it back in. So the charge is constantly flowing. That's how you do it. And what is that little man called? Well, we all know what he's called. He's called a battery. The little man is a battery. That's what a battery is. And so it's the magic of the battery that allows us to do this. Because the battery is going to create that electric field due to its voltage, right? If this material has some length L, then I know that the voltage is going to be the electric field in that material times the distance L. And so the battery is basically is that little man. And so the battery doesn't let the charge build up on one side, because it wants that. Basically, what the battery is really doing is it's keeping the energy differential. It's maintaining an energy differential. Maintains an energy difference between the two sides. That's what a battery does. It maintains an energy difference between the two sides. And it does that. And the only way it can do that is by taking the charge that would have built up on one side to cancel that energy difference, and it grabs it and it pulls it to the other side. That's what it does. And so that's the situation that we are now talking about. And batteries are not the only way to do it, I should say. This battery could also be another way to do it. We could use changing magnetic flux. d phi b dt also can do it, also does it. But that's Faraday's law, and that's what we'll talk about later. There's basically two ways to create the little man. You can either have a battery or a changing magnetic flux. But let's talk about batteries first, and let's understand this situation. Okay, and so let's try to answer this question now. So suppose I have some J passing through my conductor. So suppose I have this situation, and this current here is J, right? This flowing charge, that's J. And so suppose we have some J and E, then what is the relationship between them? What is the relationship between J and E in the conductor? That's the question. The answer, of course, is Ohm's law, but let's derive it because it's not completely obvious where Ohm's law comes from. And most of you, I know all of you have seen Ohm's law somewhere. I'll just remind you what Ohm's law is. Ohm's law is really quite beautiful. Ohm's law just says that the voltage equals current times resistance of a material. That's Ohm's law. And that gives me the relationship between current flow and electric field, and we will see that. And so that's what we want to derive right now. So let's do that. And it's actually surprisingly difficult to derive that relationship correctly using all the fancy correct physics, stat mech, quantum mechanics, blah, blah, blah. All the fancy correct physics is kind of hard. But it turns out that there's simple ways. There's very simple ways to derive Ohm's law. You might have seen them already in another class. Simple way, but let's talk about it. And so the simplest way to derive Ohm's law is to do this, is to say, okay, I got some material, a conductor, in fact. Every conductor is a material like copper, silver, gold, whatever, platinum. And here's the deal. The simplest way to think about it is that I have scattering sites, defects in the material, defects. And I turn on an electric field in the material, E. It's pointing to the right. And then what's going to happen is my charge carrier, and let's just assume we have positive charge carriers. Well, let's just assume they have some arbitrary charge Q for my charge carrier. The charge carrier is going to move. It's going to, but then it's going to hit one of those defects and it's going to bounce. And then it's going to hit another defect and it's going to bounce. And so you're going to get this bouncy, diffusive kind of behavior. And these are, we call them scattering sites, because this motion of the charge carrier it's scattering, that's what we say, it's scattering. And so it's a very bouncy kind of motion. But what we say is that there's some average velocity, and so the charge carrier is bouncing between all these things that it keeps hitting, but there's an average velocity that it has, and so this average velocity, we can call that the drift velocity. Drift velocity. And so to understand the relationship between J and E, let's take a closer look at this drift velocity and what it implies. So what we can do is we can say that there is a density of charge carriers. There's a density of charge carriers in the conductor, and that density I can say is that's the density of charge, of charge that can move, and I'll call that density N times Q, where that's the number per volume of charge carriers, and that's the charge of each charge carrier. And I want to make make an important point, which is that rho charge does not equal the total charge density in the conductor, because the total charge density in a conductor the total charge density in the conductor is typically zero, because I have just as many. The positive charge and the negative charge cancels. Instead, rho charge is equal to the charge density that can move. Charge density that can move. And this is an important distinction, because it's like if I take a chunk of copper, then if I have a chunk of copper, here's copper, like a copper wire, then the copper wire has, in the real world, the nuclei of the copper atoms is positive, and that charge cannot move. Those nuclei are frozen in place. But the electrons, are free to move in a chunk of copper. So the electrons, so those E minuses, those are the electrons. So in a chunk of copper, I could have a neutral copper where the total charge density is zero, but the charge density that can move is equal to the electrons, the electronic charge density. I just want you to understand that difference. It might seem trivial, but it's actually subtle and important. Okay, so let's continue our discussion. So now we understand this concept of charge density, charge carrier density, and so this is the charge carrier density. Then we can very easily figure out the current density, J, because J is equal to the charge carrier density times velocity, right? Times the drift velocity, V, because that's what charge density, that's what current density is. It's charge density times velocity. And so then that means that it's equal then to NQ times the drift velocity, V. Okay, but now we have to ask ourselves, what is the drift velocity? Okay, what is it? That's not completely obvious. But there's a really simple way to think about it, because the simplest thing to do is we can just say to ourselves, well, between scattering events, let's say, to understand it, we have to make an assumption. Let's assume that there's an average time equals tau between scattering events. And it's a very simple concept, but it is sort of subtle. I mean, so we're assuming that the charge carriers scatter, and then every time tau, they scatter again. And unfortunately, my tau, that's a tau, not J. I'm sorry. My taus look like my J's, and so that's unfortunate. I'm really sorry about that, but I can't fix that. So, tau. This is a scattering time tau. So what we can do then is, so we ask ourselves then, what then is the average velocity? Well, the charge carrier accelerates between scattering events. It accelerates between scattering events, and that means then that to find the velocity, we then just say, well, the velocity is going to be equal to the acceleration times tau, right? A times t, that's velocity. You guys learned that a long time ago. Well, what's the acceleration? Well, we just use F equals ma. the most important equation in physics, F equals ma. And so the acceleration is just going to be force over mass times, and then times tau. So that's the velocity. And I'm sorry, this is not a j, that's a tau. But what's the force? Well, the force that the charge carrier feels is from the electric field. And so the force is the electric field times q. I divide by the mass, I multiply by tau, and that is my average velocity. So it's actually pretty simple. And so then we say, okay, well then what's the J? What's the current that's flowing through my conductor? Remember the conductor up there. And so now we say that J is equal to nq times the velocity. So I just plug the velocity into this simple little formula right there, zoop. And so then that gives us that J is equal to, the current density is equal to nq times E q over m tau. And so that gives us this very famous formula, which is that J is equal to nq squared tau over m times E. And that's really famous because basically this is telling us that J is proportional to the electric field. And the proportionality constant we'll call sigma. J equals sigma E, where sigma is equal to nq squared tau over m. And this is the big result. And it's a very beautiful result. And it's saying that under this condition, which is, let's go back to the condition. Under this condition here, where we have the electrons bouncing on these scattering sites, then this condition leads to J being proportional to the electric field. The current is proportional to the electric field. And the constant of proportionality is sigma. And what did we call sigma? Well, sigma we call conductivity. That's what conductivity is. And so conductivity is nq squared tau over m. And so that leads to Ohm's law. So for me, that's Ohm's law. It's the same thing. So how do we get Ohm's law from this? So basically that is Ohm's law, but it might not be a familiar form of Ohm's law to you, or it might be. But let's make it more familiar. So let's notice that what we can do is I can say that J equals sigma E, but then I can just flip it and I can say that means that E is equal to 1 over sigma J, right? Then I can give 1 over sigma a name. I can say, let's call 1 over sigma rho. And I'm sorry for all these. I'm reusing rho now. This rho is not charge density. I'm using it for something different now. This rho we call resistivity, because everyone always uses rho for resistivity. It's convention. So resistivity of a material is rho, and that's 1 over sigma. And so if J, we just derived that J equals sigma E, so that means then that E I can write is equal to rho J. So it's just like a trivial relationship, but it's just very important. And so if so now let's consider a material. Let's consider some material like a copper wire that's carrying current. And let's suppose that this copper wire has some area A here, and there's some current flowing through that wire. And let's suppose that there's an electric field in this direction, and let's suppose that this wire is described by sigma. I should say that sigma is a material property. Material property. You can see that sigma, this conductivity depends on the density of charge carriers, the mass of the charge carriers, the scattering time tau. These are material dependent properties. So for each material it's different. You have to look it up in a book. Look up in book. For every material it's different. This ratio of properties. So sigma is a material property. And suppose now I have some copper wire of length L, and it's under these conditions. This is like a piece of copper in your toaster. This is every wire and every device is doing this exact same thing. So if I have the electric field is equal to rho J, then what I can do is I can say, well, let's multiply both sides times L. Let's do this. I can say E times L is equal to rho times L times J, right? I can do that, but I know that J. But then what I can do is I can do this. I can play a little trick. I can say, well, then I can multiply by 1. I can do multiply by A and then divide by A. The old multiply by 1 trick. So if E equals rho J, then this equation is also true right here. But now let's take a look at these things, because what is J times A? Well, that's just current. J times A is current. Current density times area is current. And what's E times L? Well, electric field times distance in a current carrying wire, that's just voltage, V, not velocity, voltage. And so this then leads to this relationship. I have V equals this thing, rho L over A times I. I see that the voltage across my wire is proportional. The voltage across my wire is proportional to the current, and the constant proportionality is this thing, rho times L times A over A. And what do we call that? That's otherwise known as R, the resistance. The resistance of a wire is equal to rho, the resistivity, times the length of the wire divided by the area of the wire, where rho is simply the resistivity, is 1 over sigma, the conductivity. Okay, and so now we see that we have, then this becomes R, and this becomes I, and so this then leads to our famous V equals IR, Ohm's law. Okay, so we've derived Ohm's law, now let's think a little bit more about the result of Ohm's law. So this is how you should be thinking about it. Basically, what you see then is that from Ohm's law, then we see that if I have a conductor, if there's some J flowing through the conductor, then there's also an electric field in the conductor. And there's a very simple relationship. We can see that J is related to E. J equals sigma E. So wherever I have a J, I have an E. So let's just think about this a little bit more, because we might ask ourselves, now what happens then if I have some conductor? So what happens, for example, here? Suppose I have now a conductor like this, and I have some contacts here, some electrodes here on the edges. And now I do this, I put a battery here, and that's my voltage. And so we might start, and now this is some conductor, which is basically a resistor, and now I have current flowing through it. Then I could start asking you questions. And suppose this side was grounded, just for reference. I could start saying, what is V of R? Or let's not use V, let's use, let's use this, I could start asking you questions. I could start saying, what is the potential? What is the electrostatic potential? phi in this conductor. And you would immediately start saying, you might start thinking, well, okay, well, we learned all this stuff from electrostatics. Remember, we spent a bunch of time in our class discussing this exact question. And from electrostatics, we know that, well, I remember del squared phi equals 0 was really nice if no rho total. If there's no charge density, I have del squared phi equals 0, because remember we have remember it came from del dot E is equal to rho total over epsilon naught, and E is equal to negative del phi. And so then if rho total equals 0, then I got del squared del dot negative del phi equals 0, and that gave me del squared phi equals 0. Okay, so that's what we learned from electrostatics, and then we learned all these techniques for then using this. So then we can use del squared phi equals 0 plus boundary conditions to find phi of r. Remember, we did that. So this is this was Laplace's equation. So we spent a bunch of time doing that, and so you're probably wondering, can you still use all those tricks? Do all the tricks that we learned in this class for electrostatics, do they still work? Because now everything's different, because now suddenly I have, because before we had no current. Before we had J equals 0, but now it's different. Now we have J not equal to 0. So you might be wondering, do all the tricks you learned before still work? And that's a very good question. And the answer, it's a very important question, and the answer is yes, the old tricks still work. All our old tricks still work. But it's not obvious that they would. I think it's not completely obvious. So let's show why do they still work? Why do our old tricks still work? This is why. The simplest way to think about it is because of the continuity equation. This is what comes and saves us. The continuity equation, which is otherwise known as charge conservation. They're the same thing. Remember that charge conservation, a way of writing charge conservation, that charge is neither created nor destroyed. We discussed this before in class, and we remember that if I have some divergence in the current density, then that has to be associated with a change in the total charge density. That rho is the rho total. So there has to be some change in the charge density at a point in space if there's divergence in the current density at that point in space. They have to be related, because if the current is diverging, that means it's leaving, and that means that your charge density is reducing. So that's where this comes from, and we derived that. But what's happening is that for a steady state situation, I remember for steady state, like if I have, for example, an electrical circuit where the current is just flowing in steady state, then that means that the rate of change of the charge density has to be 0. It's not changing. So that means that if I have a steady state situation where charge is flowing through a wire, then in that wire I need that the divergence of the current density has to be 0. But if the divergence is 0, then look, I remember that there's a relationship between the current flow and the electric field. Because if there's a J, that means there's an E. They're related to each other. So that means then that I can just replace the J with sigma E. Because if del dot J equals 0, then del dot sigma E equals 0. And that means that del dot E equals 0. And that has a lot of implications. I mean, the first important implication is remember that Maxwell's equations are always work. So we know that del dot E, we already know that del dot E equals the total charge density divided by epsilon naught. That's Maxwell's equations. We know that's always true. So that means then that if del dot E equals 0, then that tells us then that the total charge density in the conductor has to be 0. So that's just basically telling us that the conductor is neutral. Conductor is neutral. But also, it's telling us something else, because if del dot E, because we just derived that, since del dot J equals 0 from charge conservation, then that means that del dot E equals 0. But if del dot E equals 0, then that means that that if E is negative del phi equals 0, then that tells us then that del squared phi equals 0. So we have our old friend, yay, Laplace's equation. So this is still good. And so what that means is that Laplace's equation still holds. It still holds. So that means that all of our tricks still work. Our tricks still work. Our tricks still work. But the only difference is that now the boundary conditions are different. Because now the conductor is no longer an equal potential surface. And so the boundary conditions are different. So if I do this, if I have this situation where I have a piece of material with some electrodes and a battery and current is flowing through it, I can still use, and this is grounded here, then I can still use del squared phi equals 0 to figure out what the potential is inside of there, but my boundary conditions are different. Because this side will be V equals 0 on this side, this boundary, but on this side, or I should say, phi equals 0. Phi equals 0, but on this side, I have phi equals V, the potential of the battery supplied by the battery. So I just want to point out that Laplace's equation still works. All of our mathematical tricks still work, with just this very slight difference is that we're going to have different boundary conditions, because now we have the batteries across the conductor, and so the conductor is no longer an equal potential surface. Conductor is not an equal potential surface, but that's okay. We can still solve Laplace's equation for this new situation and figure out what the current density, what the potential is everywhere, and what the current density is. Okay, so I just wanted to make that point. Okay, so now we're going to talk about the next thing, which is now we're going to talk about the next topic today, which is electromotive force. Electromotive force. And this is one of these topics where it's like really simple and hard at the same time, like so many topics. Electromotive force is also known as EMF. EMF. And it has a simple definition, okay? So basically, it's just the EMF is basically if I have a loop, then if I integrate the electric field dot dl in the loop, that's EMF. So here's a loop. There's a loop. And so we just integrate along the loop. And if there's some E along the loop, and we're integrating here dl along the loop, then the EMF is just the integral of E dot dl. Now, what makes this subtle is because you guys already know what EMF is, because you guys already know that from before that the integral of E dot dl along a loop is equal to 0, because it's because I come back to where I started, and so that's basically the work. That's basically the voltage of the end minus the voltage of the start, and you know that that's 0. We derived that before, and this led to the relationship. This led to the relationship that del cross E is 0, because this is another way of saying that the electric field is conservative. It's a conservative field. E is a conservative field. And so why would we define something called EMF if we know already that the integral of E dot dl is 0? It makes no sense. It's nonsense. It's garbage. And so that's why I find this topic ever so slightly confusing. And so, but it turns out that under certain conditions, EMF is not 0. Sometimes, and that's why we have EMF. It turns out that sometimes the integral of E dot dl does not equal 0. Oh my God, how can that be? And so there's two situations in which that can be the case. The first situation is the first situation is when there's a battery, and the second situation is when we have a changing magnetic flux. d phi b dt does not equal 0, where phi sub b equals magnetic flux. Okay, these are the two situations when EMF does not have to be 0. And so you can see it, and you can just see it immediately. Like, so suppose, let's consider the first one, the battery. That's sort of the easier one. So let's take some itty bitty battery, and then let's take some giant current loop, some giant loop. Then suppose this battery is really tiny. I'll call that V naught. And so this is the starting point, A, and this is the ending point, B. And so what we do is we have some electric field in this wire from Ohm's law, which we just derived. There's an electric field in the wire, and because there's a J, remember, and we know that, J is equal to sigma E. That's what's happening in the wire. That's Ohm's law. But now there's some electric field in this direction, and so what we can do for this battery case is we can just integrate the electric field dot dl, and we can just integrate it for every little dl. We're just going to walk along that loop and do that whole integral from one side all the way to the other side. And then the question is, what's the answer? Well, let's assume that that the battery is really small, so that A and B are almost the same point. And so then E dot dl is simply going to be equal to V naught, the battery. Okay, so so the battery is creating this potential difference. The battery is making it so that we have this so that this current loop is so that the E dot dl is not 0. Okay, and so then we would say that the V naught is the EMF. So we can think of the battery as providing an electromotive force. The battery is providing the EMF that's pushing the electrons along. Okay, well, that's one way of thinking about it. But now there's another way. But now let's talk about the second situation where EMF can be provided by, EMF is provided by changing magnetic flux, d phi b dt. That's the new thing that we want to talk about, and basically the big result that we want to derive is that EMF is equal to negative d phi b dt. Okay, and so this is what we're going to derive, but this is otherwise known as Faraday's law. Faraday's law. And from this Faraday's law, it immediately leads to the result that del cross E is no longer equal to 0. And that makes sense because, look, let's go back up here. We saw that from before, if we have del cross E equals 0, then that immediately leads to the integral of E dot dl equals 0 from Stokes' theorem. We derive that. And so that means that if I want E dot dl to not equal 0, then I've got to make sure that my del cross E does not equal to 0. Okay, that's what I got to do. And so, okay, for a perfect loop. So let's see how this can be. Let's derive this relationship and then see how it leads to this relationship. And basically what we're going to derive is that del cross E is equal to negative dB dt. And so these two relationships are equivalent. These are two equivalent ways of writing Faraday's law. So this is what we want to derive, and this is the big thing that we want to do right now. So let's derive this. Let's see. How can this be true? So to see how this is true, what we're going to do is we're gonna create a situation where we have changing magnetic flux. And there's two different ways to do this, and they're really equivalent. Changing magnetic flux. What we're going to do is we're going to take the flying loop approach. We're going to do it using the flying loop, like a frisbee, flying loop. The flying loop approach. So the flying loop approach is basically just saying, suppose we have some how to draw this? Suppose we have some magnetic field which is not constant in space. It can be like, it's just changing in space, some magnetic field. So those are the lines of magnetic field, B of R, it's changing in space. And what we're going to do is we're going to take our flying loop and we're going to throw our frisbee and we're going to say, suppose I have a loop of wire, and just for argument's sake, let's suppose that there's some current flowing through it, I, and let's just say that I equals lambda U, where that's the current where U is equal to the velocity of the charge carriers, velocity of charge in the rest frame of loop. In the rest frame of the loop. And lambda is equal to charge per distance in the loop. It's the density of charge carriers per distance. That's a concept that you guys have seen before. You know that I is equal to lambda U for a one-dimensional wire. And so we're taking this loop and we're throwing it like a frisbee into this magnetic field, and it's moving. And so at time t1, it's sitting here, and the magnetic field is creating some flux. I'll call that phi 1 through the loop, and the flux is equal to the integral of B dot dA. for the loop. And so I have to define some normal vector so let's assume that there's some normal vector, and I can, where dA is equal to differential area times n hat in the usual way. And then, but then at some later time, it's moving through the air. I throw it through the air and it has some velocity. And so it has some velocity. I threw it. And so at some later time, it's here, T2. And now it has a new magnetic flux. I'll call it phi 2, which is now equal to also B dot dA, but now it's in the new location, so the B field is different. And so we can see then that that the change in flux d phi is equal to phi 2 minus phi 1. Okay, so that's the change in flux over this time. And I could say d phi dt, I could do it like this. I could say d phi dt equals phi 2 minus phi 1 divided by dt. And so this is one way that the magnetic flux is changing in time. And because we see now that we get a change d phi dt in the magnetic flux, where phi in this case is flux. Phi equals magnetic flux. Now that's one way to get changing flux. Another way I should just say right now would be I could have a static loop, and I could have the static loop just sitting there, and then I could have the B changing in time. And now that I have some B field here, and the B field is changing in time. And that's another way, the static loop case. But the point that I want to make, and maybe this won't be completely obvious to you at first, but think about it, and then you'll see that it's true. The point I want to make is that the flying loop is equivalent to the static loop. So whether you approach this from the flying loop perspective or the static loop perspective doesn't really matter. You can always, one is always the other, is the same as the other. Because look, if I'm doing the flying loop and I'm flying through some inhomogeneous B field, my flux is changing. But if I'm standing on the loop, if I'm a little man standing on the loop, then from the little man's perspective, the loop is stationary and the B field is changing. So the point is that from mathematically, they're sort of equivalent. So either way is a perfectly valid approach, way to go. So we're going to approach this topic from the flying loop perspective, which might seem unintuitive because it seems, like in the laboratory, our electrical circuits are not usually flying through the air, but it just turns out that the flying loop is easier for the derivation. The math is easier for the flying loop. Okay, so let's see if we can so basically what we want to do is we want to derive a relationship between the changing magnetic flux in the flying loop and the electromagnetic force, the electromotive force in the loop. We want to derive this relationship for the flying loop. That's what we're about to do. Flying loop. And so let's do that. So now to do that, I'm going to draw it again. And so we're going to start looking at the details. And so we'll assume that there's some B field. I'm going to draw the B field sort of like this. There's some B field everywhere, some inhomogeneous B field. And then we have our loop, which is flying through the air with some velocity. I threw it into the B field. But now what I'm going to do is I'm going to look at the loop, and let's just assume that there's some current flowing through this loop, and that current is I equals lambda U, where U is the velocity of the current in the rest frame of the loop. I told you that before, same as before. And what happened, and the current and the loop has some area, and let's assume that there's a normal vector I can do perpendicular to the surface of the loop. And so now what I can do is I can say, well, this is the loop at some time t1, at t equals, I'll call it t naught. But now what I want to do is I want to look at the loop a little itty bitty time later. So what happens if this is my velocity? Let's assume that this is my velocity right there. That's my velocity. So my loop is flying through the air with some velocity v. I didn't draw it so well. Try to get them parallel. So my loop is flying through the air with some velocity v. Then what happens at some little bit of time later? Loop at t equals t naught plus dt. That's what I want to know. So this is what happens. At some little time later, I can see that the loop has moved some little distance, dt. And what I can do is I can draw the loop here. Let's draw it. And so this is my loop, and so I can make this funky drawing. It's not that funky, it's simple. If I could only do it. There's my loop. Oh, terrible drawing. There's my loop, and so you see that it has traveled this distance. So I'm just going to draw it like this so you can just see that. And this is the loop. And this is the loop at some time t, slightly time t later. And so in this new location, and so what I can see is that I have a pancake. So there's a volume here. The volume, this situation creates a pancake. The volume can be thought of as a pancake. Volume is a pancake. This is equivalent to a pancake volume. And so I can think of the volume where I have the loop at time t naught and the loop at time t naught plus dt, and I can think of that as the volume, and here there's some ribbon around the loop, and this distance, well, you know what that distance is. That distance is v dt, right? This distance is v dt. That's the thickness of the pancake, and so let's think of it like that. And so if I define this geometry, this pancake geometry defined by the area of the loop at t naught and at t naught plus dt, then I can take that volume and I can just do, let's just do the magnetic Gauss's law. Magnetic Gauss's law, which no one really talks that way, but let's just call it that, because the magnetic Gauss's law is simply saying that the integral of del dot B over any volume d tau that means the volume is equal to 0. We know that, but because since del dot B equals 0, but that means then that because that's an integral of a divergence over volume, that means that the integral of B dot dA over a closed volume over a closed surface is equal to 0. So we know that to be true. That's the magnetic Gauss's law. And so let's do this integral for this weird little pancake volume that we've just defined. And so if I do that, then I can see then that 0 is equal to the integral over the area at t naught B dot dA over the top surface plus the integral of B dot dA over the area, but at the later time t, the bottom surface, t naught plus dt. So this is the top surface, and this is the bottom surface. But then I also have the ribbon, the side, the ribbon, which I call the ribbon. I'm going to call this the ribbon. Ribbon. So plus the integral, to do it correctly, I got to do b dot dA over all surfaces. And this is going to be over the side, the ribbon. Ribbon, which is the side. And so if I do b dot dA on all three of those areas, then I add them up, they got to equal 0. Right? They do. And so if we do that integral, then I see that the top integral, I do like this. Let's keep that picture there. It's the integral of b dot dA n hat, that's this n hat right here, right? For the top surface. But then if I do the bottom surface, and that'll be area over A, but then for the bottom, I got the dA is pointing in the opposite direction. So for the bottom, it's going to be plus integral b dot dA minus n hat. And then I can say plus plus the integral over the ribbon, b dot dA equals 0. And so then what I can do is what I notice is b dot dA n hat, this one, that's going to be my magnetic flux phi b at time t naught. And this integral here is going to be minus negative of my magnetic flux at t naught plus dt. And then this is just my flux of the ribbon. I'll just keep that one, ribbon, b dot dA equals 0. And so what I'm going to do now is I'm going to take this, I'm going to put it on the other side, and I'm going to multiply both sides times -1, and that's going to then give me this equation, phi b, the magnetic flux through my flying loop at t naught plus dt minus the magnetic flux at t naught is equal to the flux through the ribbon, b dot dA through the ribbon. Okay, and so what we can do now, and eventually this is going to lead us to Faraday's law, but what we have to do now is and you can see that things are starting to look good, because this is basically, this is going to be my d phi, but I need to get dt. Where's my dt? we'll get it soon. So we see that the trick now is, what is the flux through the ribbon? We got to get that. And so to get the flux through the ribbon, what we're going to do is we're going to do a little bit of geometry, because I want you to, we're going to go back to this picture of the ribbon here. Maybe what I'll do is I'll redraw it, because this is the situation. I'll draw it here. I have, this is my ribbon. I'll exaggerate it. It's flying through the air. This is v dt, and this is my bottom loop. That's my pancake, and that's v dt. And so what I can do is, I remember that there was some current flowing through this. Remember, let's not forget about there was some current equals lambda u. And so what I can do is let's just do some geometry, because what we realize is that I have this vector here is v dt, and if I'm integrating, if I'm integrating the ribbon here, then I have to integrate along the ribbon, and so I can break the ribbon into these little chunks. I'll call that dl, right? And so what if I break the ribbon into little chunks, then you'll notice that doing some little clever geometry, I have a parallelogram. And so I can think of the ribbon as made up of all these little parallelograms. So this is kind of clever geometry, but it's not that clever. You've seen this kind of stuff before. And so that's the area of this ribbon is these little parallelograms. And so I can ask myself, what's the area of this little parallelogram? And we can notice there's some very cute little geometry, because we can notice that the area of that parallelogram, dA, is equal to, if this is the angle between it, theta, then you can see that dA is equal to v dt times dl times sine theta, right? That's the area of the parallelogram. But then we also need, but we also need a direction, and notice there's something very cute, which is that this is actually the magnitude of v dt cross dl. Oops. And so, but then we also can notice that if I want to turn my dA into an actual vector dA, then I can keep the cross product because it gives me the right direction. V dt cross dl. Oh, I keep going dt. Jesus Christ. And so this is what we just derived. And you can see from the right-hand rule how it gives you the correct thing, the correct direction, since dA is perpendicular to surface. So it's really cute. The cross product gives us everything we want. So dA equals v dt cross dl. And that's where our dt is going to come from. d phi dt, that's where our dt is coming from. So now what we can do is this very cute little trick, and we can say that this d phi, which is this thing here, we can now say that the change in magnetic flux through the loop, d phi, is equal to, and now I can do this integral over the ribbon. The integral over the ribbon, it's going to be b dot this thing, v dt cross dl. v dt cross dl. Isn't that nice? That's so cool. Such a cute little mathematical trick. And now we'll just go a little further, and and now we'll pull this dt over here, and then we'll pull it all the way under. Let's pull it under. And so let's divide both sides by dt. Divide by dt, and we're going to get d phi b dt is equal to the integral over the ribbon, and it's circulating the whole ribbon, so I'll draw it like that, over the ribbon of b dot v cross dl. I did it again. Can't seem to stop doing that. dl. Okay. So that's a really cute little relationship that we've derived. And so now, since we're doing all this vector stuff, so let's put a little box around that. That's really cute. And basically what we want this to be, we want to, to get the right answer, you know what we got to do? We got to show that this thing is equal to negative EMF. And how are we going to do that? Well, let's do it. I'll show you. There's some more little tricks in store. Let's notice that um, let's notice that let's go back to the drawing, and let's notice that the charge carriers in the loop, the velocity is u. That's the velocity of charge carrier in loop. But notice that the loop is also moving through space with this velocity v. And so a charge carrier in the loop, which is carrying some current I, the velocity of the total velocity of charge carrier in the loop is equal to, I'll call it now, W equals U plus V. So W, the total velocity of a charge carrier in the loop, is equal to U plus V. And that makes sense because it's moving with some U in the loop, and the loop is moving with some velocity V. I'm just adding the velocities. I think that's not tricky. Okay, but now let's get a little tricky, because now let's notice a little mathematical trick. Math trick. And our math trick is that let's just notice that W cross dl is equal to U plus V cross dl is equal to U cross dl plus V cross dl. Okay, so far nothing looks too tricky, but now comes the tricky thing. Notice that U and dl are parallel. See, let's go back to our thing here. So here's the U is parallel to the dl, because the dl, see here, back to this drawing up here, the dl is moving along the loop. And so what I want you to see is that dl and U are parallel. They have to be. dl is always pointing in the direction because the current is flowing in the loop. And so dl and U are always pointing in the same direction at every point on the loop. At every point on the loop, U and dl are parallel. And so what that means is U cross dl has to equal, can you guess? 0. Because the cross product between parallel vectors is 0. And so that allows me to derive this seemingly trivial relationship, which is actually useful for this derivation, which is W cross dl is equal to V cross dl. Now, why is that useful? Well, this is why, because let's plug this into this equation up here. I'm going to plug it into here. In this equation, I'm going to replace the V cross dl with W cross dl, and you'll soon see why I did that. So now let's do that. d phi b dt is equal to the integral over the ribbon of b dot W cross dl. And I can do that since W cross dl is exactly equal to V cross dl. Okay, well, why did I do that? Well, you'll soon see, because now let's use another little math trick, another little trick. And this other little trick is this. Let's use that, it's a very trivial trick, one that you all know. B dot W cross dl is equal to negative W cross B dot dl. That's just a simple dot, what do you call this, triple product or dot cross product? I forget. This is just a simple math identity, a vector identity that you've all seen many times. So I'm just using this very simple vector identity. And so that means that I can rewrite this equation as d phi b dt is equal to negative integral over the ribbon of W cross B dot DL. W cross B dot DL. Okay, now we're almost at the end. So we have to ask ourselves, what is this W cross B? Well, we have to realize that the force on charge moving in loop, the force on a charge carrier in loop is equal to Q times the total velocity of that charge cross B. That is the force on the charge in a loop. Okay, so that means that the charge that's flowing through this loop is feeling that force. Let's go back to this loop. Here we are. And so now the force that the charge flowing through that loop feels is Q times W cross B, where W is the total velocity. Remember, W is equal to U plus V. That's the flying velocity and the current in the loop velocity. But this is, okay, and so that means then that the force per charge in the loop is W cross B. Now let's define this as F is equal to force per charge in the loop. Now what is force per charge? Think about it for a moment. I know that if I have an electric field, then electric field creates a force on a loop. Force is equal to E times Q. And so then we see that F, force per charge, I can write as F over Q leads to, is the same as E, an electric field. That's what an electric field is. An electric field is a force per charge. So this W cross B, which is equal to F, my force per charge, is equal to an effective electric field, E. An effective electric field. So what I can do then is I can say that d phi dt is equal to negative, and this is integral over the ribbon, the effective electric field dot dl. But and so now what I can do is let's move that negative sign. I'm going to erase it from this side. I'm going to put it onto this side. So now this is my equation, but what is the integral of the effective electric field dot dl? Well, I'll be damned. That is my EMF. That's what the EMF is. And so that is the EMF. That's the EMF felt in that loop. And so what we have just derived is that EMF is equal to negative d phi dt, where EMF is defined as the integral of E dot dl over a loop. And that is what we have just derived, and that's a big deal. We just derived it. That's Faraday's law. Faraday's law. Very significant, very big deal. And so let's just very quickly, that's the hard part. Now let's do the easy part, which is that's basically, let's just remind ourselves the geometry, what we've just derived. So let's consider the geometry. We've done the hard part. And so what we've just derived is this. We have a loop. There can be some current flowing in the loop. And if I have some magnetic field, stupid thing. If I have some magnetic field like this, B, then we've just derived that the integral of we've just derived that the integral of E dot dl in that loop, I did it again. The integral of E dot dl in that loop is equal to negative d phi dt, where phi is the magnetic flux. Okay, and so this is what we just derived. But this is for an arbitrary size loop. This is remember, this is for any loop, any arbitrary loop. And so let's take a closer look at this equation, because what we can do then is we can say for any loop, then I have I have an area of my loop, and I can do Stokes' theorem. And so I know that the integral E dot dl is going to be the integral of del cross E dot dA for that loop over the area of the loop. Area. And then the magnetic flux can be written as negative d dt of the flux, which is also an integral over area. It's b dot dA, right? And so this equation turns into this equation. So this equation turns into this equation. And then what I can do is I can bring that derivative into the integral. And so then I can see that I have the integral over the area of that loop of this quantity, del cross E dot dA. And I can see that that is equal to the integral over the area of my loop of this quantity, negative d dt of B dot dA. Okay, now look at this equation and realize that this is for any loop. And so what I can do then is shrink the loop really tiny, shrink it tiny, and then what you get is that these two things then have to be equal, because it's for any loop. So that means that these interiors have to be equal for this to be equal for any loop. So then that means that I have del cross E is equal to negative dB dt. And this is a gigantic big deal. This is a new Maxwell's equation. So that's a new Maxwell equation. Faraday's law. And it's a really big deal, because basically it's telling me that we used to think that del cross E is zero for electrostatics, and it is equal to zero for electrostatics when nothing's changing. But we see now that del cross E is equal to negative dB dt when things are changing. And when things are changing, we call it electrodynamics. Dynamics means changing. Things change. So we see that the more correct equation is this one, is that del cross E is not always zero. If the B field is changing, it's not. It's del cross E is negative dB dt. And let's just consider the geometry of it just for a moment. The geometry is that, remember this one. This is the one that is easier to remember. We all remember this, that del cross B is equal to mu naught J, right? And so this one gave us a geometry that we all are familiar with from right-hand rule. We see that if I have some current density J, then that creates curl in my B field. So this is a geometry that you guys remember. So what we do is we say that J creates curl. J creates curl in B. Okay, we all know that. That's the one that is kind of easy to remember. But now the new one is this. Now I want you to see that del cross E, the new equation is del cross E is equal to negative dB dt. And this equation is very confusing when you first see it, but I want to try to demystify it a little bit. I want you to see that this part is sort of like playing the same role as current. It's playing the same role. This plays the same role as J in Ampere's law, because this is remember, this is Ampere's law. Ampere's law. And we see that what's happening is that the dB dt, the negative dB dt, is playing the same role as J in Ampere's law. And so what that means is that now if I have some negative dB dt pointing in some direction, then that creates curl in E. And so I can say that negative dB dt creates curl in E, creates curl in E. And so it's it's the same geometry. I want you to see the geometry, like, see, I'll circle this. The geometry there is the same as this geometry. You can use the right-hand rule, because if I have some dB dt, then by the right-hand rule, that's going to create curl in my E field. The same way that if I have some J, it creates curl in my B field. So I want you to see that curl in the E field is equivalent to negative dB dt. But negative dB dt is equivalent also to curl in the E field. You can't, if you have one, you got to have the other. To get curl in my E field, I got to have a changing magnetic field. If I have a changing magnetic field, then I got to have some curl in my E field. They go together. They go together. I hit those. They go together. I want you to see that geometry. Okay, that's where I'm going to stop. Thanks. Bye-bye.